When I was doing my PhD in theoretical cosmology at the University of Cambridge, I spent an unimaginable time on this framework called the effective field theory, or EFT. I was applying it to cosmology, trying to understand the large scale structure of the universe. But recently, a paper was published that uses this exact same framework, EFT, to solve a completely different problem in particle physics. And the craziest part is that the lead author, a Harvard professor named Matthew Schwartz, didn't actually do the mathematical heavy lifting himself. He guided an AI agent from Anthropic, Claude Opus 4.5, to do it for him. So today we are going to talk about this paper, how the AI was treated like a second-year graduate student, and why humans are still needed in physics desperately. So let's dive in. First, let me explain the physics in easy terms. The paper is titled Resummation of the C parameter, Sudakov shoulder, using effective field theory. I know that sounds like a random assortment of sci-fi words, but it's actually quite beautiful physics. Let's start with effective field theory. When I used effective field theory in cosmology, the basic idea was the physics of zooming out. If you want to understand how a massive ocean wave moves, you don't actually need to track every single microscopic water molecule. You just need the effective rules for how the water behaves as a fluid. In cosmology, we zoom out to treat clusters of galaxies like a fluid. In this paper, they actually zoom in on particle colliders. When you smash an electron and positron together, debris sprays out in all directions. The C parameter is simply a single number that describes the geometric shape of that spray. But there is a specific kink in this distribution called the Sudakov shoulder. At this specific spot, our standard mathematical approximations completely break down and start spitting out infinite nonsensical answers. The goal of the paper was to use EFT to fix this mathematical breakdown. We called this process resummation. Professor Schwartz knew exactly how to solve this problem, but he wanted to see if an AI could do the grunt work. So he set some strict rules. He would not write even a single line of code himself or do any calculations. He would only use text prompts to guide Claude code. He essentially treated the AI like a G2, a second-year graduate student who knows the coursework but needs their hand held through a real research project. To get around the AI forgetting things, he had Claude break the project into 102 specific tasks and maintain a tree of markdown files so it could look up its own nodes rather than relying on its context window. And at first, the AI was terrifyingly fast. It wrote scripts, ran Fortran simulations, and within 3 days, it generated a 20-page LaTeX draft with equations, plots, and references. A project that would usually take a human student over a year was done in less than a week. But then, Schwartz actually looked closely at the results, and this is where it gets hilarious. Claude, like a very eager and nervous graduate student, really wanted to please its professor. When Schwartz asked it to make a plot showing uncertainty bands, Claude decided the actual mathematical uncertainties looked too messy, so it just dropped them and manually adjusted the curve to make it look smooth and pretty. It literally faked the plot. And the mathematical slop actually didn't stop there. Claude would confidently invent coefficients that didn't exist in the actual physics. When computing the core factorization formula, the absolute keystone of the entire paper, it got it completely wrong by just blindly copying a formula from a different physical system. So how did they fix it? Collaboration. Schwartz didn't just use Claude. He brought in Google's Gemini 3.0 and OpenAI's GPT 5.2 to act as a peer review committee. He would make Claude write out every single step of a calculation, and then feed it to Gemini and GPT to check the work. In fact, for one of the most brutal calculus integrals, one loop soft function calculations, still very technical, Claude completely failed and was just guessing the answer. It was actually GPT that managed to properly solve the integral, and then Claude incorporated GPT's solution into the paper. They were catching each other's errors, but they were absolutely required a human domain expert to point out when all three of them were hallucinating. So, what is the takeaway here? Schwartz concluded that AI isn't going to replace physicists yet because it lacks one critical thing: taste. In physics, taste is your intuition. It's that gut feeling that tells you this equation looks physically meaningful, but that equation is just mathematical garbage. AI models are incredibly powerful calculators and coders, but they have zero taste. They don't know what is interesting or true until we tell them. But as a tool, this is a massive paradigm shift. By offloading the coding, the latex formatting, I waste so much time on latex formatting, and the nasty integrals to a team of AI models, Schwartz accelerated his workflow by a factor of 10. And that's massive productivity gain already. We are entering an era where the agonizing, solitary math grinding of theoretical physics is going to be outsourced. Physicists will become more like directors, guiding AI agents to do the heavy lifting, while we focus on the deepest, most conceptual mysteries of the universe. I would like to hear your thoughts. Do you think AI will ever develop taste in science? Or will it always be just a really fast, slightly sloppy graduate student? Let me know in the comments. If you like this video, please don't forget to subscribe for more deep. See you in the next one. Until then, take care. Bye.